In this lecture, which probably is going to be relatively short, we're going to finish finally our discussion of simple linear regression. Okay, so the last thing that we discussed in the previous lecture was how do we assess accuracy, or how well the linear model fits our data, and that was R squared. But another thing that we need to do with linear regression is to perform the diagnostic. See, even if the model fits the data nicely, it may still be of limited use. So we have to look more carefully at the errors, at the residuals. Here's what I mean. You can pretty much see how the errors are distributed, right? So I can, if when I'm looking at this graph, at the scatter plot, you can see that probably the highest points density is close to my straight line, right? My regression line. And as I go further away from the line, above and below, I can see that the density of points actually is dropping. This is good, right? This is a good indication. Say, for example, I would have a different distribution of points. What if, when I was looking at my scatter plot, I had very little points, almost no points around my straight line, but there was a cloud right here, some distance above my straight line, and cloud down here, some distance again below my straight line. That would mean that I'm actually predicting, so my in this case my straight line equation would predict prices which are kind of in the middle, right? But at the same time they don't predict anything specifically well, because most points are either way above my regression or way below my regression, right? No points come even close to the regression. So therefore I have to look at the distribution of the errors. So let's go ahead and calculate the errors first. Calculation of the errors is very simple. So this is going to be look probably a little weird. Here's what I'm going to do. I'm going to take all of my points, right? How many points did I have in my data set? I believe it was 100 points, right? 100 cars. So I'm going to take all of these cars and I will use the regression equation, this one right here, okay, in order to make predictions about the price of each and every car in my data set. So in other words, for each car, and I can do that because I know mileages of all of my cars, right? So for me to predict the prices, all I have to do is take all the mileages for each and every car and plug them in, right? And I will calculate an alternative price for the car, if you will, right? The one from this straight line, okay? So you can say, well, this is stupid, right? What's the point of doing that? We know the actual prices. They're included with the mileages in your data set. So why would you want to predict the prices that you already know? Aren't you supposed to use this model to predict the prices of the cars that you don't know? That the only thing that you know about them are the mileages? Isn't that was the original intent? If you know the mileage, you can predict the price. True, right? But at the same time, I'm going to predict the prices for already documented cars with known prices, in order to evaluate how large are my errors, okay, and how are they distributed. If my errors in general are going to be small, okay, and mostly centered around 0, that means that my model does pretty decent job predicting the car prices, right? But if my errors will be distributed in a weird looking way, then that can give me the clue actually how my model can be improved. So without further ado, let me go ahead and predict the prices for the cars that I already know the prices for. So I'm going to call them predicted prices, okay? Predicted car prices. And prediction of the car prices is done very simple. There is a function called predict. Alright, and all I have to do really is give that function the data set for which I want to predict my, sorry, not the data set, the model, okay? the model. So I will use the model that I built. How did I call it? Called simple linear regression model, right? And actually, if I run this line right now, that's enough, okay? Because what it will do is it will take my linear regression, this one right here, okay, and it will use the same exactly data set, cars data, and it will extract all the mileages for all 100 cars, plug that into the equation, and it will give me 100 predicted lines, 100 predicted numbers, right? So let me go ahead and do that. So if I run this line right now, okay, that's it pretty much, right? There is no output. All the predicted prices for the cars were recorded into this. It's actually a vector variable, right? It's one single name pointing to 100 different predicted values. So let's take a look. Predicted car prices. So if I run that line, it shows me all 100 predicted values, right? So for the car number 1 from my data set, it predicted the price $14,748, right? For the car number 2, $14,253, etc., etc. For the last car, $14,815, right? So these are the predicted prices for the exactly same cars that I have in my dataset. In other words, these values are nicely forming this straight line. Okay, that's what I got from this function, right? And now what I need to do is calculate the errors. Now the errors are going to be again called residuals, right? That's how statisticians call errors. And they're going to be just differences between the actual car price, this one for example, minus its corresponding predicted value from the straight line. So this distance, vertical distance from the point to the line, is the error. Some errors are going to be positive, some errors are going to be negative, right? The car price was below the regression line, then the distance is negative, and therefore the error is negative. Okay. So here's how I'm going to calculate residuals. Residuals. I'm going to even call them like that. Residuals equal. And that's actual minus predicted, right? And how do I get actual? Actual, I'll actually record it in the dataset cars data. And this column is called price, right? So that's what I'm going to do here. I'm going to say cars data, $price. These are the actual values minus predicted car prices. And now I run this line, and apparently I got everything, right? So let's print out residuals like that. And again, because I have 100 cars, I have 100 errors, 100 residuals. So you can see that some residuals are negative. So for example, for the very first car, residual was minus 0.148. Apparently it's, I don't even know, quite frankly, where is the first car on this line, because here they're aligned according to the mileage from lowest to highest, but the first car did not necessarily have the lowest mileage, right? So I don't know where it is. So the price for the first car apparently was lower than the predicted price, right? That's why my residual was negative. So for the first car I was off by 148. That's thousands of dollars, right? So the error was I overpredicted by 148. For the second car, I overpredicted by $153. Then by 186. For this car, I overpredicted, I underpredicted actually by $417, right? So this is the meaning of these values. So each of them is just basically by how much I was off, right? So these are residuals. By the way, while we're on the topic, I could calculate residuals in a simpler way, okay? Let me call it residuals 2. Residuals 2, okay? Alternatively calculated residuals. I'm going to get exactly the same values, okay? So all I have to do is call the function resid, this one. It's the function that calculates residuals for me. And all I have to do is feed the model into the function. So I'm going to send simple linear regression model into the function, and it will return again 100 errors or 100 residuals. So let's go ahead and do that. Okay, like this. Alright, so now I'm going to show residuals 2, and you will see that the values are exactly the same. So residuals 2. Okay, first one minus 148 and minus 153, minus 148 minus 153, so we get the idea. But either way is fine, right? Either use just built-in function provided by R, or calculate the predicted prices and subtract them from the actual prices. Either way gives you the same exact thing. Okay, so how do we perform diagnostic of the residuals? Here are a few conditions. I need to create another scatter plot, but on my first scatter plot I had car prices as my y variable, and I had mileages as my x variable, right? For the residual plot, I can still use mileages as my x variable, right? And I have to use the residuals, the errors, okay, that I'm making in predicting the prices, as my vertical y variable. And this is how my ideal residual plot should look like. As you can see, it should be random cloud of points, about half points. The center of the cloud, horizontal center of the cloud of points, should be 0. So in other words, in about half cases I have under-predicted the price, and about half other cases I've over-predicted the price. Okay, so half of my residuals should be positive, another half should be negative, right? So there should be balance right there. Also, as you can see, the cloud of points, let me show you on the next slide, it should have uniform thickness everywhere. Okay, so this is the ideal residual plot. And another important consideration is that I should not have any detectable patterns in my residuals. So in other words, residuals should not be all negative at the beginning and then 0 and then they become positive. So I can see like a trend going on, right? Going up or down. I should not see any curves such as first residuals were negative, then they were positive, and then they were negative again. So there is like a parabola, curvature going on in the residuals, right? It should be uniform cloud, horizontal cloud, with no lines, trends, curves, nothing identifiable. And it should have uniform thickness everywhere. So that's one condition. If I have residuals that are looking like that, let me actually go back, right? So piece of terminology, okay? If I see this pattern where the thickness of the clouds of points is uniform, right? Doesn't increase, doesn't decrease, it stays the same, then this is the situation which is called Homo Scadasticity. This is what I normally should see in the residual plot. If on the other hand I have pattern like this, so in my case, like for example, the more mileage I see on the car, the bigger the variability in the prices, or other way around, the more mileage is in the car, the lower the variability in the prices. So in other words, I have some sort of the conical shape going on like this, okay? Increasing variability or decreasing variability. This is something that's opposite to Homo Scadasticity. This is called Heteroskedasticity, okay? Change in the variance. So the residual plot has different thickness at different regions, right? That is highly undesirable pattern. Okay, that is an indication that your model predicts, for example, talking about cars, right? If I see this pattern, that means that prices for the low mileages are fairly consistent, and the higher the mileage, the more inconsistency in the predictions, right? The errors become larger and larger and larger, right? So the more mileage is on the car, the more error I'm making, right? So my model does not predict the prices uniformly well, so to speak, right? In some regions it works better than in other regions, right? If I have this pattern, it's opposite, right? The variability of the prices for low mileages is pretty high, right? But as the car gets older and more mileage on it, then cars prices have less, less variance in them, right? And therefore my model starts to work better and better and better. It gives me lower and lower and lower errors. So again, model works differently for different values of the prices. Okay, so it doesn't have consistent performance. There are ways in statistics to battle this phenomenon. Okay, you can do it, for example, with the log transformation, but that is beyond the discussion in this course. Okay, so this is for more advanced statistical or data analytical courses. Okay, so important thing to remember is when I do the diagnostics of the residuals, right, here are the things that I'm looking for. First of all, the residuals must be normally distributed. Okay, again, normal distribution. Remember when we discussed at the beginning of the semester that normal distribution has a special meaning in statistics, right? And indeed it does. So we discussed that all the majority of tests that we performed, we can perform them only when your samples or differences between matching pairs in the samples are normally distributed, right? Only then you can use t-distribution to perform t-tests. Normal distribution shows up right here again, right? It says that for your model to be nice and applicable, your residuals should be centered around 0. Should have it somewhere. Yeah, I don't see it here. So the average residual should be close to 0, right? That means that your average error that you're making is not positive, it's not negative, it's not biased in under prediction or over prediction of the prices. The average error is 0, right? So that's one thing. Second, your residuals must be normally distributed. Okay, they should not show any sign of heteroskedasticity, so nothing like that. It should be a cloud of points with uniform thickness, right? Also, it should have no visually identifiable patterns, such as trends up or down, lines, any types of curves. So anything that is different from the horizontal cloud is a bad sign. Okay, that means that probably straight line or linear regression does not fit your model nicely. Okay, it may benefit if you do some other models, non-linear models. And again, non-linear models are not part of our discussion here. In this course, we concentrate only on the linear regression. Okay, so let's go ahead and perform all these beautiful tests on our data set. So I'm going to switch to RStudio. Okay, so I calculated my residuals. Let me get rid of residuals too. It was just to illustrate that there's another way to calculate the same residuals. So let me go ahead and plot the scatter plot first, right? So I can go ahead and say, how do we plot, how to make scatter plot? Well, we use the function called plot, right? So here I'm going to say scatter plot of residuals. All right, and there are multiple different ways actually how I can plot. So I'll show you a couple of them, right? So number one is I can, so again, my y variable will always be the residual, right? The errors. So I'm gonna say let's plot. Let's create a scatter plot. So x first, I'm going to get mileages. Okay. So I'm going to say cars data mileage. All right, and plot the residuals versus mileage. So I'm going to get mileage, and that's my x, and my y is residuals, like that, right? So when I run this function, there it is. Okay, so again, horizontally I have mileage, right? So all cars are ranging from low mileage to high mileage, right? And here vertically I have residual. So it looks like pretty good scatter plot, right? First of all, I believe the 0 is the center of my plot, pretty much, right? So I have, roughly speaking, half of the points above and half of the points below. The average appears to be 0, right? thickness of the residual plot is uniform, right? So here I have from roughly minus 0.5 to about 0.6. Here's the same thing from roughly minus 0.5 to about 0.6, right? So I don't see any variability changes, right? No conical shape. So therefore this is a Homo Scadastic plot, right? It has Homo Scadasticity, does not show any signs of Heteroskedasticity, right? And also there are no patterns, right? So I don't see residuals trending up or trending down or showing me some sort of the curves, right? Or sine waves, sometimes that can happen, right? So it's a well-behaved random plot. Okay, so this is one way how I can plot that. Another way how I can plot it is same residuals, but I'm going to rearrange them kind of. So instead of plotting them against the mileage, I can plot them versus the price, right? So I can see, like, what if I'm going to, well, let me just show you, right? So I'm just going to use different variable horizontally. Okay, instead of mileages, I'm going to plot the residuals versus price, right? So how residuals behave for the cheaper cars versus more expensive cars. Okay, so I'm going to say, let's do the plot. So this time around, my X is going to be from the data set cars data. I'm going to use price as my horizontal X, and Y is the residuals themselves. Residuals themselves. Okay, so now I can see some weird stuff, right? Now I can see that the residuals, now this is what I call a pattern, right? I'm kind of glad that I did that. So what do I see? I see that that might be a sign of the problem, right? My model does not behave all the same for different cars, right? So when the cars are on the when the price of the cars is on the low side, right? So probably cars with high mileages, right? Then my model, look at that, all residuals here tend to be all negative, right? With a few exceptions, right? So in this part of my plot, all the residuals are negative. Okay. In the middle of the plot, I have pretty much a balance of positive and negative, right? And then over here, for high prices, right, I have all residuals to be positive. Well, with a rare exception, this point right here, right? So that is the pattern, right? So there is a trend line in my residual. Quite frankly, I didn't see that coming. That might be a sign of the problem, right? So what does that mean, really? It means that for the price for the cars that are priced low, my model tends to have negative errors, right? And negative error means what? Actual minus the predicted is less than 0. That means actual is less than the predicted, right? So I over predict. My model tends to over predict the price of the car for the cheaper cars with high mileage on them, right? It works okay in a balanced way for the middle priced cars, and for more expensive cars which probably have less miles on them, right? The residuals tend to be positive, which means that the actual is above the predicted, right? So my model is under predicts the prices, right? My model over predicts the prices for cheaper cars, and it under predicts the prices for more expensive cars. So that means that my model doesn't work in a stable way in all the regions, right? So that's how we are supposed to analyze the residuals plot. Okay, so see if there are any potential issues with the residuals. All right, so and another thing that I have to check is, are my residuals normally distributed, right? Remember, that was one of the conditions for the whole model to be usable. All right, so well, first let's do the same thing as we always do for normality check, right? Let's do histogram first. I'm going to plot residuals, normality histogram for the residuals, like this. Okay, there you go. So what do we see? It's actually a pretty nice looking plot, right? Well, maybe not perfect, normal, but at least it's unimodal, bell-shaped. Average seems to be around 0, so that's pretty good. All right, and now I'm going to check the residuals using rigorous Shapiro-Wilk test. So I'm going to Shapiro-Wilk check residuals for me. Normality, residuals, residuals, like this. Okay, so when I run this test, it gives me the p-value 0.2892. So it's above 5% significance level, which means that the null hypothesis stays, and null says that the residuals are normally distributed, right? So therefore residuals are normal, and I don't have an issue from that standpoint. Okay, so this is part of the regression diagnostics. Okay, so that concludes our coverage of topic for simple linear regression. And in the next couple of lectures, we're going to concentrate on a more complicated case. So the idea is going to be exactly the same, right? We're going to try and model certain target variable y, dependent variable, based on predictor variables x. But this time around, our predictors are there are going to be several predictors. Okay, so in this example, we used simple linear regression because there was only one predictor, right? The mileage. That's it, nothing else. So we're going to throw more variables into the mixture in order to predict maybe our target more accurately. Okay, so the analysis that we're going to perform will be largely very similar to what we did here. So we covered all basics. Okay, again, we're going to look at which variables are significant and which are not significant based on the hypothesis test for the slope for each and every predictor variable. That's one thing. And we're going to look at r squared, only this time around is going to be called adjusted r squared, and we'll discuss what's the difference between adjusted r squared and the regular r squared that we used here. Okay, then we're going to look at the residuals plots. We're going to check residuals for normality, for patterns, but also we're going to also take a look at another test which is called multi-collinearity. So all of that is coming in the next couple of lectures. All right.